Hi, I'm Zor. Welcome to Unizor Education. I would like to talk about logarithms. It's kind of natural sequence after we were talking about exponential functions. All right, this is an introductory lecture, and I'll talk about definition of logarithm and its very basic properties without any details and no difficult stuff at all. All right, so let's start with exponential function. I would like to remind a couple of things about exponential function. Number one is the function is defined for positive a and not equal to 1, because 1 to power of any power will probably result in 1, so it's not really an interesting function. So we are talking about a function of this type. Now, it's obviously defined for all real values of x, and y is also real, and it's greater than 0. I'm just reminding basic properties of this. Another basic property is that the function is monotonic. It's monotonically increasing with a greater than 1, and it's monotonically decreasing for values of a less than 1 and greater than 0, of course. Now, if you refer back to the lecture about monotonic functions, I was actually talking about monotonically increasing functions, but it doesn't really matter. It's equally applicable to monotonically decreasing as well. You know that monotonic function establishes the one-to-one correspondence between domain and the range. And in particular, it follows from this monotonicity of the function and the fact that it's one-to-one correspondence, there is an inverse function. So there is always inverse function in this case. Well, good. So there is an inverse function with in this particular case, and if the exponential function establishes the relationship between all real numbers, one-to-one correspondence actually between all real numbers and positive real numbers, then inverse function establishes the one-to-one correspondence between positive real numbers and all real numbers. Well, actually, this function is called the logarithmic function. So, if you know how to find from a real number x a to the power of x, which is equal to y, and we know that there is an inverse function, it means that if y is given to you, you can always find such an x that a to the power of x would be equal to y. Well, now, since we're talking about reverse function, and usually x is used as an argument and y as a function, so we can talk about function which is the following. It's symbolically written as this, and what it means actually. It means that you have to find such a value of the exponent, which is y. If a is raised to this power, you will get x. So if a is raised to the power logarithm x base a, it's x. This is a definition. It's not a theorem, it's a definition. logarithm of some value x, and it should be positive since we're talking about the range of this function. So logarithm of the positive value x, base a, is a value which if used as an exponent with the base a will give x. So since this is a definition, there is nothing to prove about this, but what we can say is that this function also establishes the one-to-one correspondence. In this case, between all the values where the result of this function can be, which is positive real values, it's one-to-one correspondence with all real values, which can be the value of the logarithm. So this is logarithm, x by the value a. From all positive real values establish the one-to-one correspondence and monotonic, by the way, function to the all real values. All right, so that's basically the definition, not too much to it. Now let's talk about monotonicity. Now we know that the monotonic function, this monotonic function, is increasing when a is greater than 0. Now if the function increases, then inverse function is also monotonically increases, right? I mean, it's obviously. I can prove it actually. It's very easy to prove. Monotonic function is if u less than v, then f at u less than f at v. Now, the function which works backwards, let's call it g function. Let's use, so basically g function transforms f at u into u, and it transforms f at v into v, right? Now, so if this is less than this, and it's given, then this might be less than this. Because if it's not, then we can apply the function again, f, and back to these values, and it will be an opposite relationship. So it cannot, so if this is less than this cannot be greater or equal or anything like that. Because then the function would not be in the same relationship as we were actually talking about. So this is elementary stuff. Now, since we have established that logarithmic function establishes the monotonic one-to-one correspondence between all real positive real numbers and all real numbers, it's monotonically increasing whenever the exponential function is increasing. So you know that exponential function is increasing when a is greater than 1 and decreasing when a is less than 1. So similarly, inverse function is increasing when a is greater than 1 and decreasing when a is less than 1. Now I think it's time to exemplify whatever I was talking about. And I have a couple of examples. What is logarithm base 2 of 256? Now, what did we know about logarithm? Logarithm of a number is a power which is, if used with this base, will give this number. So, what the power I should raise the 2 to get 256? Well, 8, all right? 2 to the power of 8 is 256. That's why this is equal to 8. Because 2 to the power of 8 gives you 256. It's directly from definition. I didn't really calculate anything. I basically guessed. Yes, I guessed the value of this function. I guessed that if I will take 8, then knowing that 2 to the power of 8 is 256, this is the right value. And there is no other value because it's one-to-one correspondence, there is only one value, it's one monotonic function. Now, next example. Logarithm base 10 of 0.01. Okay, what is it? Again, what power should I use with the base 10 to get 100ths? Well, remember that 100ths, this is 10 to the power of minus 2, right? That's the definition of negative 2 as a power. So, that's what I have to do this. Again, I kind of guessed that if 10 is raised to the power minus 2, I get 0.01. That's why minus 2 is the value of this logarithm. And the third example I have is logarithm of 1 base 2.5. I don't want to scare you. I put base 2.5, it's kind of not exactly the nice number, but I put 1 here. Now, let's just remember that any number to the power of 0 will give you 1. Remember this, right? So that's why this is equal to 0, because 2.5 to the power of 0 will give 1. So always, whenever you see something like this, it signifies the power into which I have to raise the base to get the argument. Okay? Now, as a couple of particular cases, special cases with logarithms, there are certain bases which are more preferable than others. Primarily, base 10 is very often used in different calculations. So whenever we are talking about function with base 10 as a logarithm, there is a special notation about this function. It's either no base at all, and 10 basically is assumed. Sometimes in some, I think it's non-English literature, they use just LG as this particular type of logarithm. And it's called common or decimal logarithm. Now, another type of logarithm. Okay, there is a number which is called E in mathematics, which is approximately 2.721. It's actually an irrational number, and it's very important in mathematical analysis for different purposes. I'm not talking about the purposes right now, I'm talking about the logarithm which has the base E. It has a very, very important function in analysis, and that's why there is a special notation. The logarithm is with the base E is called natural logarithm, and its notation is ln. And it is natural. Believe me, there are many different reasons why this particular logarithm is called natural. All right, so these are just basically just the terminology. Now, I would like to present a very important property of logarithm, which is probably the most important property, and I would actually be willing to say that this property is the reason why people kind of invented logarithms and used the logarithms. And here is the property. Now, you remember this property of exponential function. Now, if you don't, I refer you to previous lectures about exponential functions. This is a typical kind of a thing. Just for example, 3 to 15ths is equal to 3, 3, 3, 5. No, sorry. 12. Something like this. So, exponents are added together whenever you multiply the exponential expressions. Now, great. Let's call this u, this v. Actually, let's do it a little bit differently. Let's call this u, this v, and this w. So, what can I say? Well, w is equal to a to the power of p plus q. Now, what does it mean? P plus q is an exponent, the power actually, I can raise a to get w. What is this? This is, by definition of logarithm, the power I should raise a to get w, right? Which is the same thing, right? So it's p plus q. So from this, I can write this. They mean exactly the same thing. This is a definition of logarithm, basically. If you have this, p plus q is the power I have to raise a to get w. P plus q is, by definition, logarithm, is a power I have to raise the base to get the argument. That's the same thing. Similarly, p is logarithm u at base a. Why? Because if I raise a to the power p, I will get u, right? That's what it is. Again, this is just the definition of logarithm. I didn't do any logical derivation here, just a specific definition. And similarly, q is logarithm v to the power of a. So, what do we see here? Well, p, q, p plus q, right? So, using the right side of this equation, I would say that logarithm u plus logarithm v with the same base, this plus this, is equal to this, which is logarithm power base a of w. But w is u times v, right? From this, w is u times v. So here is basically the formula. In logarithms, this formula is equivalent to this one in exponential functions. The logarithm of the product is equal to sum of logarithms, assuming the same base everywhere, obviously. Same thing as this. The exponent of a sum is equal to product of exponents. It's, in some way, it's similar. But this is the function, this is inverse function, and that's why the property actually is inverse. From summation we go to product, from product we go to summation. Kind of symmetrical, right? Now, my claim is that this property is so important that it actually is the reason why logarithms exist. Now, here is why. A couple of days ago, it's just a personal example, by the way. A couple of days ago, I wanted to calculate some probability. And it was something like, what's the probability of, let's say, 80 people out of 100 having some property. So, in the calculation of this probability, I had to calculate something like this. Now, this is factorial. It means 1 times 2 times 3, etc. times 100. This is the product of all numbers from 1 to 80, and this is the product of all numbers from 1 to 20. How can I possibly calculate this? There is absolutely no way. I can't even program it in the computer because it will go outside of the range of the computer program, outside of the computer memory or something. However, I can use this particular function. By the way, similar to this, I can say that logarithm of u divided by v is equal to logarithm u minus logarithm v. I will basically prove this. It's very easy to prove. But in any case, what I will do, instead of calculating this, I will calculate logarithm of this. Logarithm of this result of this division, it's equal to logarithm of 100 factorial minus logarithm 80 minus logarithm 20 factorial. Now this is 1 times 2 times 3, etc. times 100. So instead of doing this, instead of multiplying 1 by 2 by 3, etc., I will basically do summation. It's logarithm 1 plus logarithm 2, etc. plus logarithm 100, right? Because the logarithm of a product is equal to sum of logarithms. Similarly, this also, this is a sum. This is a sum. And this is a sum. Now, once I did this, I can calculate it, I can put it into any program, and the program will calculate without any problems. And then, after I have figured out what my logarithm of this is, all I have to do is I have to raise 10 into this power to get the value of this. So, without logarithms, I wouldn't even be able to do this calculation even with the computers because the numbers are too large. With logarithms, by converting whatever the very complicated expression you have into its logarithms and calculating in the logarithm and then exponentially transfer it back, that's how the calculations are made. Basically, again, this is, in my personal view, this property is the justification for existence of the logarithms. So, what's the main let me sum up whatever I was talking today about. To sum it up, I can say that number one, you have to understand the definition of the logarithms. And the definition basically is in this formula. A to the power log x base a is equal to x. This is a definition. What power should I use for a base a to get x? That's the logarithm of x by the base a. That's number one. And number two, another very important property is this. Logarithm of product is equal to sum of logarithms. These are two main properties of the logarithm which you really should remember and keep it always in mind. Everything else can be derived from this. Just as an example, from this we can very easily derive this. Okay. This is the property. If under the logarithm, under the argument, you have some kind of a power of something, then the power can be brought outside of the logarithm, and whatever remains, the base of this exponential function, would be an argument of the logarithm. Now, if you have, for instance, natural exponent here, let's say u to the n's. This is u times u, etc. times u, right? So if I will take logarithm of this, it will be equal to logarithm of this, and this is the logarithm of a product, right? Which is sum of logarithms. It's all base a. And this is n times, right? Because the product a to the power of n is the product of n times n times product of u by itself, which is exactly equal to n times log u by the base a. So as you see, the exponent is brought outside of the logarithm. But this is for natural n, because then we can write a to the power of n as u to the power of n as u times u times u. Now, what about any power? Power, as you know, an exponential function can be any real number. And this particular property is still true, and here is why. Now, let's go from the definition. As I was saying, the definition and elementary properties is enough. What is this? This is, let's call it w is equal to log u to the power of delta times a. What does it mean? It means a to the power of w equals to u to the delta, right? That's what it means. A to this power gives you an argument. Well, if I'm claiming that this is equal to this, well, let's check. We have to check that a raised to this power should equal to this. If I will prove this, then I will prove this. Because this is exactly the same thing. If I would like to show that this is logarithm of u to the power of delta by the base a, I have to prove that a to this power gives me u to the delta. Now, is it true or not? Well, again, you remember the property of exponential functions. I hope you remember this. If you don't, again, go back to exponential functions lecture. A to the product of two numbers is a to the first number and the result to the second. Or they can be reversed, actually. It doesn't really matter because the product is commutative. So sequential raising into power basically results in the multiplication of the exponents. So here, I'm using this property. Instead of delta would be p, instead of log u by the base a, it would be q. So I will use this thing. So this is my pq. Q is this, so it's a to the power of log u base a to the power of delta. Delta is t. What is this? What is log u by the base a if a I raise into this power? This is a definition of a logarithm definition of log u, because this is the power. I should raise a to get u. So let's raise a to this power. I will get u, right? So this will be u still to the power of delta. So that's a very simple proof, actually, which is based only on the definition of logarithm and this property of exponential function. And basically that's how I would like to finish this introduction. This is just an introduction because the properties of logarithms are much more numerous, and there are some interesting problems which I will solve with you. Thanks very much for listening to this lecture. I do encourage you to go into unizor.com and basically take the whole course. This is just one small part of it. And it would be great if you can register and take exams. That's very, very useful, so I do recommend it to you. Thank you very much. Hi, I'm Zor. I would like to continue talking about logarithms, and primarily, right now, this is about graphs. So, graph of the logarithmic function. The key to this point is the fact that logarithmic function is an inverse function to exponential function. Now, we all know how exponential function looks like. So if this is exponential function, its graph is for a greater than 1, it goes like this, and for a less than 1, it goes like this. So, just if necessary, just refresh your memory and go to the lectures about exponential function. Fine. Next, we have to understand that logarithmic function is an inverse, by definition, of the exponential function. And as I was explaining in lectures about monotonic functions and inverse functions, the graph of the inverse function is symmetrical to the graph of the original function relative to the angle bisector between x and y axis. So this is angle bisector. Now, symmetrical relative to this line. Well, let me try. Symmetrical to this one would be something like, symmetrical to this point would be this point, also 1. Symmetrical to this would be this, and symmetrical to this would be this. So this is y is equal to log x a, where a is greater than 1. Now, symmetrical to this line relative to this axis would be this. So these two lines symmetrically are these two lines. So this is y is equal to log x, where a is less than 1 and greater than 0. So basically, I finished. I mean, these are graphs of the logarithmic function. In as much as exponential function asymptotically approaching the x-axis, the logarithmic function will asymptotically approach the vertical y-axis here with a greater than 1. With a less than 1, it's the other way around. Same as the exponential function is asymptotically approaching the x-axis. It would be here, this. Okay, now, if this is the qualitative, so to speak, picture of how the graph of the logarithmic function looks like, then there are certain quantitative issues. And the most important quantitative issue is the following. What happens with the graph of the logarithmic function if a is changing? Well, let's go again to the graph of the exponential function. Now, for greater than 1a, the exponential function is increasing. Now, if a is greater, then the exponential function would be growing faster or diminishing faster, because the base is greater. So let me just use this. This is greater a. Now, similarly, so it looks like the whole graph actually is turning this way when a is growing. Now, the corresponding logarithmic will also be turning, but actually the opposite, because it's symmetrical, right? If this goes this way, symmetrical goes this way. So most likely I will have to have something like this. As a graph. So as a is growing, exponential function turns this way, symmetrical logarithmic function will go this way. And actually I would like to algebraically prove it. What I mean is, if I am in this area of the argument, x greater than 1, then the greater base will correspond to a smaller logarithm. That's what I would like to prove. Purely algebraically. And here's how we do it. Let's consider, first of all, that the base is greater than 1, and I have two bases. I have this base, which is a, and this base, which is b. And b is greater than a, and both are greater than 1. So we are talking about the logarithmic function which is increasing. Okay. Also, I would like to consider first this particular interval, x greater than 1. And I would like to prove that under these conditions, the logarithm of the x base a is greater than logarithm x base b. How can I prove that? Here is how. One of the properties of the logarithmic function, and allow me to wipe out this, because we don't really need this graph anymore. We have already drawn it. Now we are algebraically trying to research it. Okay. Now, one of the properties of the logarithms which we were talking about was the following. Logarithm ba times logarithm xb is equal to logarithm xa. Remember mnemonics which I was talking about? B over a, x over b. B is reduced, so we have x over a. Again, this is just mnemonic. You don't have to think about any kind of meaningful relationship between this and this. So anyway, in this particular case, let's think about this. This is logarithm a, this is logarithm b, and it looks like I'm multiplying logarithm by the base b by something to get this. Now, how about this? Well, obviously, log ba is greater than 1 since a is less than b. Now, why is that? This is the bigger number, this is the smaller number, so obviously I have to raise it to a power greater than 1. Well, but we can actually do it more more strictly if you wish. Now, the way how to do it strictly, so if you have b greater than a, then you know that a to the power log b a is equal to b, right? Because that's the definition of the logarithm. So what we can say is a to the first degree, first power, is less than b, and b I will represent as this one. Now we know that exponential function is monotonically increasing for a greater than 1. Now, since it's monotonically increasing function, we know that increase of the argument is always coming together with increase of the function, and increase of the function comes together with increase of the argument. So if I know this, it means that my exponential parts are also in the same relationship. So 1 is less than logarithm. Logarithm is greater than 1. So, proof that. What do we see now? We see that this logarithm x at the base b should be multiplied by something greater than 1 to get this. Which means, obviously, that this is greater than this. Log x a is greater than log x b. Since I have to multiply this by a factor greater than 1 to get this, it's supposed to be less. So, let's just think again what we have proven. That this graph of the logarithmic function, if I take a different base b, if a is less than b, then the logarithm goes above. So its logarithm at this base is greater. Now, on this particular segment, from 0 to 1, situation is reversed. So the logarithm of the bigger base should be higher, which means greater than the logarithm on the smaller base. Now, how can we prove that? Actually, we will just reduce one problem to another, as mathematicians usually do. So, again, we have this, and now we have x in this interval. And we would like to prove that logarithm of the bigger base is greater than logarithm of the smaller base. Now, how can we do this? Well, very simply. Don't forget that x is less than 1, and if you remember, logarithms of any number which is less than 1 are negative, right? So instead of doing that, I will use another variable, let's say t, which is equal to 1 over x. Now, if x is in this particular interval, then t is obviously greater than 1, right? It's inverse. Now, but I know that if I consider this and this, whatever I have just proved before was this. Now, these are positive numbers because t is greater than 1. And this is, I have just proven this, right? But now let's think about back to the x terminology, what is t? T is 1 over x, right? So let's replace it with this, and let's replace it with this. And now let's remember that logarithms of 1 over x is minus logarithm of x, right? That was one of the properties in the previous lecture. So minus log x a is greater than minus log x b. Now, we don't need these minuses, right? And if you remember, if we multiply the inequality by minus 1, then the sign of the inequality should be changed to the opposite, right? So log x a is greater, change the opposite, less than log x b. And that's exactly what needs to be proved. So, what we have actually done right now, we not only built the general form of the graph, but we also quantitatively evaluated it. So let me again draw the graph. This is 1, and this is general form of y is equal to log x, where a is greater than 1. So it's increasing. Now, I don't even want to talk about the graph when a is less than 1, because it's completely symmetrical, and all relationships are obviously symmetrical as well. So, not only we have drawn this qualitative picture, so to speak, but we also have the quantitative evaluation. If a is growing, then the graph is turning this way. So this goes to this, and this goes closer to this. So that actually kind of gives you a very nice picture of how the graph behaves. There is one more very interesting detail about this. Some time ago, when I was talking about exponential functions, I was talking about graph and the tangent at the point x equals 0. This tangent for greater base, this is a to the power of x. The greater base a, the graph is steeper. And now, what I also pointed out, that somewhere between the values of 2 and 3 for the base, this particular angle is exactly 45 degrees. Now, the value when it is equal to 45 degrees is actually irrational number e, which is approximately 2.71. So the graph of the function e to the power of x has this tangent exactly at 45 degrees. Now let's consider the symmetrical graph, symmetrical relative to the bisector of the angle between the axes. Now this is also 45 degree, and this is 45 degree. So this line should be parallel. So the tangential principle is supposed to be preserved between this line and the tangent. So if I will have a tangent here, for logarithm which is based the same number e, and if you remember I called it natural logarithm, and there is a special notation for this. Natural logarithm is logarithm base e, where e is this irrational number. Should also have this tangential line, this tangent, at 45 degrees. So whenever your base of the logarithm is greater than e, is 2.71, etc. So let's say it's 3 or 4, etc. It's increasing. Then the graph should go in such a way that this tangent goes a little bit, it's tilted down, like in this particular case. And whenever you have smaller base than e, let's say logarithm by the base 2, for instance, yes, it goes actually above, tangential line will be greater than at 45 degrees. So this is the complete picture of the graph, and that basically is all I wanted to talk about as a theoretical material. I mean, I also had a couple of problems, but these are easy. So next lecture, probably more than one, I will devote to different problems related to logarithms. So good luck, register and take all the exams which are available on the website on unizor.com, and until the next time, thank you very much. Hi, I'm Zor. Welcome to Unizor Education. Today we will solve some problems about logarithms, which have been explained in the previous couple of lectures. We're talking about definition of logarithms, main properties, graphs, etc. So this lecture and maybe one or two others we will devote to solving problems with logarithms, which is extremely important to basically understand the concept much better. This lecture will be about very simple problems, which are very, very basic. They are based on the definition of the logarithms. So allow me to basically spend some time on this, because I believe it's very important to really feel how the whole thing with logarithms is working before we go to anything more complex. So, simple problems. Okay, I have a set of problems which are formulated as follows. Given the following equality, what's necessary is to rewrite this equality in exponential form. So basically we have to think about what logarithm actually means. What's the definition of the logarithm? Okay, the logarithm of 9 with the base 3 is the power, we have to raise 3, the base, to get 9. Now obviously this is 2, because 3 to the power of 2 is equal to 9. So basically these two forms are equivalent to one another. And to convert one into another, you really have to understand what logarithm is about. So again, since this is a power which 3 is supposed to be raised to get 9, and obviously 3 to the second power 2 is 9, so that's why it's equal to 2. Similarly, logarithm of 8 base 1, 2, 1 second. Now, this is minus 3. Why? Again, let's think about the definition of the logarithm. It's supposed to be the power I have to raise the base, which is 1 half, to get 8. Okay. Is it true to the power of minus 3? Will it give me 8? Well, obviously it is true, because minus means we have to reverse the 1 half into 2, and 2 to the power of 3 would be 8. So this is an equivalent to this. Let's go further. Log base 1/10 of 1 thousandths is equal to 3. Again, if I will raise the base, which is 1/10, to the power of 3, I will get 1/10 times 1/10 times 1/10 is 1,000. So this is justification for this. That's why this can be rewritten as exponential form. These two are completely equivalent. Next. Okay, let me wipe out this. So I will preserve the large format. I have 3 more of the same type. These are illustrative problems just to show what the definition of the logarithm actually is. Log base 1, no, sorry, base 2. Of 1, 10, 24 equals -10. Well, what does it mean? It means 2 to the power of -10 should be equal to 1024, right? 1, no, sorry, again, it's 2, not 1/2. To the power -10 equals 2. Now, what is 2 to the power -10? Minus means 2 should be inverted into 1/2, and then 10 times multiplied by itself. Well, you can verify it is 1024. Well, I was working with computers for a very long time, and in computers, powers of 2 are very important for some reason. So I just remember that powers of 2, I remember up to probably 12 or even more. So, these are completely equivalent. This means that 2 to the power -10 is equal to 1024, and this means exactly the same thing. A little bit more strange looking. Log-based square root of 3 of 1/3. What is this? -2. Well, let's think about it. If I will have -3 to the power, square root of 3, sorry, to the power of -2, what does it mean? Well, minus means I have to invert it. It would be 1 over square root of 3. And then square, well, square root of 3 square would be 3, so it would be 1/3, which is exactly this. So again, this means that square root of 3 to the power of -2 is equal to 1/3, and this means exactly the same thing. And the last one in this series, log 3 of 1 over square root of 3 is equal to -1/2. Well, let's do this. 3 to the power -1/2. What is it? Well, 3 to the power of -1, let's say it would be 1/3, and then 1/2 means square root. So it will be square root of 1/3, which is 1 over square root of 3. So these two forms, these two are completely equivalent to each other. They are actually a definition of the logarithm. I didn't calculate anything. I have just rewritten one into a different format. Meaning of these two things is exactly the same. This means that the 2 to the power of -10 is equal to 1024. This means exactly the same thing. 2 to the power of -10 equals to 1 over 1024. The same meaning, different notation, no more than this. What actually I wanted to emphasize is that logarithms are just a different notation for exponential function. Nothing more than that. Alright, so this series of problems we have finished. Next one is actually very similar, but in reverse. Now we have to rewrite in the logarithmic form something which is given as exponential. So if I know that 10 cubed is equal to 1000, how can I rewrite this exponential expression in logarithmic form? Okay, let's just think about it. I know that 10 to the power of 3 is equal to 1000, right? Now that means that if I will get logarithm base 10 of 1000, I should get 3. That's what it means. This is a definition of the exponential expression, basically, notation of the exponential expression. This is exactly the same expression written differently, written using the logarithm. The meaning of this notation means exactly the same as the meaning of this notation. Again, 10 to the power 1/2 is equal to square root of 10. Or, alternatively, we can say that log base 10 of square root of 10 is equal to 1/2, which means 10 to the power of 1/2 is equal to square root of 10. 2 to the third degree is equal to 8 means same thing as log base 2 of 8 is 3. Log base, so the base here becomes the base here. The result of this raising to the power is supposed to be under the logarithms, and the exponential part itself becomes the value of this logarithm. 8 to the power 1/3 is equal to 2, which means log base 8 of 2 is equal to 1/3. 1/3 is actually a cubic root, so cubic root of 8 is 2, obviously. One half to the power of -3 is equal to 8. It's exactly the same as log base 1/2 of 8 is equal to -3. Both are correct. Indeed, minus means we have to invert 1/2 into 2, basically, and then cube would be 8. Same thing there. And the last one in this series (4 to the power -1/2 equals to 1/2. Well, is it correct, by the way? 4 minus means it's 1/4. 1/2 means square root. Square root of 1/4 is 1/2. Exactly. So, in the logarithmic notation, it means log base 4 of this equals whatever the exponential thing is. Okay, that's the last one in this series. So we have converted logarithmic expression into exponential and exponential into logarithmic. In both cases, my most important point is that these are exactly equivalent to each other, just different notation of the same thing. Now, let's assume that all logarithms below are base 1/2. So, what's the logarithm of 1/2? Well, here's an interesting consideration. When you have an exponential function, let's say 2 to the 4th is equal to 16, you can just calculate. If you don't know this value, you can calculate it. Well, you multiply 2 by 2 by 2 by 2, you will get 16. This is a calculable thing. what if I will say an equivalent thing? What is log 16 2? Well, here you have to make a little guess, basically. Well, which power should I use to raise the 2 to get 16? Well, you just think about, well, 2 power of 2 would be too small, because 2 squared would be only 4. 3 also too small. 2 to the third power is 8. Finally 4, okay, 2 to the fourth power, yes, this is 16. So you're kind of guessing the answer to this problem. You cannot directly calculate it using whatever your... I'm not talking about calculators, I'm talking about just using your mind. So you really have to kind of guess that this is 4. You have to try and fail and try and fail, and finally you get the result. Now, this is a very important difference between logarithms and exponential functions. Exponential functions in simple cases. I'm not talking about exponential functions of a complicated case like this. No, I'm talking about integers, basically, which are relatively easy to calculate. Integers and inversed to integers things. Now, this is something which you really have to, well, think a bit, just a little. Now, which power should I use 1/2 to raise 1/2 to get 1/2? Well, obviously, in this case, it's an easy answer. It's 1. Indeed, 1/2, let's just make, it's checking, basically. To the first power means it's just by itself, so it's 1/2. So this is correct thing. Since this is correct, and this is equivalent to this, then this is correct. Next. Power. Which power should I use for 1/2 to get 1? Well, again, this is an easy thing, because I know that any number raised to the power of 0, by definition actually, the power of 0 is 1, right? So I know that 1/2 to the power of 0 is equal to 1. So that's why this is equal to 0. This power, which I have to use 1/2 to this power, get me 1. Next, log 1/2 of 2 equals. All right. Now, just a little bit more complicated. What power should I use for 1/2 to get 2? Well, again, it's kind of easy for me, since this is less than 0 and this is greater than 0. It means I have to invert it, so my power should be negative. And considering I'm basically talking about easy problems, it should be negative and integer. Well, my first try and very successful one would be -1. Well, indeed, if you will do this, what does it mean? Raise 1/2 into the power of -1. It's basically an inversion. From 1/2 I'll get 2. Exactly what I have to have here. So 1/2 raised to the power of -1 gives you 2. This is exactly the same thing. That's why this is a correct answer. Okay, next. Log base 1/2 is usually of 1/8. Well, let's think about it. What power should I use to raise 1/2 into to get 1/8? Well, the power of 1 gives me 1/2, power of 2 gives me 1/2 times 1/2, so it's 1/4. And finally, power of 3 gives me 1/2 times 1/2 times 1/2, and that would be 1/8 actually. So it should be 3. And this is the verification. 1/2 to the power of 3 is equal to 1/8. Oh, I'm sorry, 1/8, not 8. Next. log base 1/2 of 8. Well, let's think about it. If using the power of 3 I get 1/8, then using the power minus 3 I should get an inverse of 1/8, right? And indeed 1/2 minus 3 is equal to, minus means it should be inverted, so 1/2 becomes 2, power of 3, 2 times 2 times 2 would be 8. So 1/2 raised to the power of minus 3 gives me 8. Now, again, let me emphasize, I guessed it. Well, I mean, in this case, maybe not my first guess, but one of the first guesses was actually a successful guess. Obviously, this would not work for something more complicated, but for these little exercises, that's exactly what's necessary to do. You have to just approximate what might be the answer, positive or negative versus what exactly the relationship between these two base and expression under logarithm. If they are less than 1 and greater than 1, then the power should be negative. If they are the same, both less than 1 or both greater than 1, then the power should be positive. This should be positive. Finally, the last one in this series, log 1/2 of 1/64. 6, right? Because 1/2 to the 6th degree would be 1/64. Because it's 2 times 2 times 2 times 2 times 2 times 2. It's 2 times 6 times by itself in the denominator, and that's 1/64. Okay, that's the last one in this series. Just takes a little guessing, as you saw. With logarithms, as I was saying, you have to do a little guessing in these simple cases. You cannot directly calculate, like if you have some integer exponent, and you can basically multiply things directly. And now I have the last series of the problems, which is exactly the same as the previous one, but now the base is 25. So base is 25 of 1/5. Okay. As I was saying before, this thing is greater than 1, this thing is less than 1, so most likely, I mean, definitely, not most likely, definitely our exponent, the power we have to raise 25 to, should be negative. So 25 becomes 1/25. Now, how to get from 1/25 1/5? Well, you have to really extract the square root, right? Square root of 25, which is the power of 1/2. So my guess is it's minus 1/2. Let's just think about it. 25. If you will raise it into 1 minus 1/2, what does it mean? First, you have to invert it because it's minus, so it's 1/25. And 1/2 means square root. Square root of 1/25 is 1/5. Exactly what we have to get here. So 25 raised to the power of minus 1/2 is 1/5. That's why this is the correct answer. Next, log base 25 of 6/25. Well, this is obviously 2, because 25 square is 6/25. All right, log base 25 of 5. Well, obviously this is 1/2, because 25 half, which is square root of 25, it's 5. Next, log 25 of 1/25. Well, what power should I use to convert 25 into 1/25? Obviously minus 1. Because 25 in the power of minus 1 is 1/25. right? Two more. As you see, these are all simple problems, and they're basically are nothing but repetition of the definition of the logarithms. So if you know the definition of the logarithm, that this is the power you have to use to raise the base to get the expression under the logarithm. If you know this, every one of these problems is trivial. Okay, I have two more. Log 25 of 1, 625. Okay, you remember that log of 625 was 2, because 25 to the power of 2 was 625. If I want 1 over 625, it should be minus 2, right? Because we have to invert it. And indeed, 25 to the power of minus 2, it's 1 over 1/25 squared, which is 1 over 625. And the last one, which I'm sure everybody considers as an easy thing, the logarithm of 1 base 25 or base 1/2 or base anything would always be 0, because any base to the power of 0 will give 1. So this was the last problem, and again, the whole lecture is short and simple, and its only purpose is to basically inculcate into your minds the definition of the logarithm. It's just a different notation for exponent. If you know this, you know that. Nothing new about this. With calculations of the value of the logarithm, here situation is slightly different, because in simple cases, calculation of the exponent is actually simple. Calculation of logarithms involves certain guessing. But that's only in simple cases. In practice, doesn't really matter, because people don't really do anything right now outside of the computers. But in these simple cases, when integers are involved, you really have to understand that the guessing is really fine in this particular case. All right. I do encourage you to use unizor.com as a complete course, actually, which introduces you to different aspects of mathematics, and it would really help development of your analytical thinking, your creativity, etc. So do consider registering under certain supervision, get enrollment in some course like algebra or geometry or whatever, because then you will be presented with an opportunity to go through exams. Exams are important. Here I am explaining this, and it's kind of easy for you to follow, but if you have to really do the exam yourself, it really trains your mind relatively well. Thank you very much. Hi, I'm Zor. I would like to continue solving problems with logarithms. These problems are also simple, so just try to solve them themselves first, and then listen to this lecture. So that's probably very important for you to try to do it yourself first. But anyway, the problems are very simple. So let me just go straight ahead with whatever I had. The first series of problems is related to equations which is necessary to solve. So, log base 3 of 3 plus x equals 2. Now, all these equations are basically illustrations to definition of the logarithm. So, what's the definition of logarithm? Well, you know that if base is raised into the value of this logarithm, which is 2, you will have the value under the sign of logarithm. So from here, and using the definition of the logarithm, we can derive that 3 plus x is 3 to the power of 2. So 3 plus x equals 9, x equals 6. That's the solution. And indeed, if you will substitute x here, you will have 3 plus x, which is 9, and logarithm 9 with the base 3 is 2, because 3 squared is 9. So all of these examples are on the same level of difficulty. I'm just thinking that the more examples, more equations of this type we will solve, well, the better you will feel about the logarithms, and more fluent you will be in this language. Next, log base 1/2 of x over 2 equals -3. Again, using the logarithm's definition, the base 1/2 raised into the power -3, which is the value of the whole logarithm, should be equal to whatever the value of under the logarithm is, right? So 1/2 to the -3. Minus means it should be inverted, so it's 2 to the power of 3, which is 8. 8 equals, and x is equal 16. And again, if you substitute 16 here, you will have 8, and logarithm of 8 base 1/2 is -3, because 1/2 to the power of -3 will give you 8. By the way, don't think that all problems with logarithms are that simple. These are just illustrative problems. There are much more complex ones, which probably we will address in the next lecture or so. Log of log base 110, 5x equals 3. Okay, let me be a little bit faster in this case. So 1/10 to the 3rd degree is equal to 5x. This is 1/1000 equals 5x. X equals 1 over 5,000. That's the solution. So, as you noticed, I'm saying less words and more actions, because it's actually, I've already said all the words. Everything is supposed to be understood right now from just whatever I'm writing about. Log 2 x to the 10th degree is equal to -10. So 2 to the power of -10 should be equal to x to the power of 10. Well, it's easier if you will do it this way. 2 to the power -10 is 1/2 to the power of 10. And considering that exponential function is really the graph, well, this is not, I'm sorry, this is not an exponential function, but the graph of this function, x to the 10th degree, is something like this. It looks like a parabola, but steeper. So in this particular case, it's very easy to find one solution, which is obvious solution. X is equal to 1/2. But as you understand, x equals to -1/2 is also a solution, because this is an even power. -1/2 to the 10th degree is exactly the same as 1/2 to the 10th degree. So we have two solutions to this equation. Log 1 of base square root of 3 of 3x is equal to -2. All right. So square root of 3 to the power minus 2 is equal to 3x. Now, this is 1 over square root of 3 to the second degree, which is 1/3. So 1 over square root of 3 square is basically squaring of separately numerator and denominator. 1 square is 1, square root of 3 square is 3. So from here we have x is equal to 1/9, right? All right, done that. I hope I'm not boring with all these very, very similar and very simple equations. But again, I'm just trying to say that the more problems of this you solve, the better you will feel about it. This is the last equation. By the way, just looking at this equation, you already have to understand that x is supposed to be greater than 0, because otherwise the square root would not exist, and then 1 over square root prohibits x equals to 0. All right, so 3 to the power of minus 1/2 is supposed to be equal to this. Now, this is 1/3 to the power 1/2. This is square root of 1/3 is equal to 1 over square root of x. Now we can square both sides, and that would be 1/3 equals to 1 over x, x equals 3, which is indeed positive value. That's why it fits the bill. Well, that's it about equations. So next series of problems is calculation. So we will try to calculate, obviously without the calculators, certain things related to logarithms. I think this is a little bit more interesting. Log base 3 of 3 square root of 3. Now, how to calculate this? Well, here is how. First of all, you have to express the value in parentheses as the power of 3. If you will do that, then obviously logarithm is equal to a. We know that from theoretical lectures, and we talked about this many times. Because 3 to the power of a would be 3 to the power of a, right? That's the definition of the logarithm. So all we need to do is to transform the value in parentheses into base to some power. Well, but that's very easy to do. 3 is 3 to the first power. Now multiply by square root of 3, which is 3 to the 1/2. Now, whenever we have two numbers which are actually which are exponents with the same base and different exponents on the top, what you have to do is you have to add up the exponents. So this is 3 to 1 plus 1/2. I hope you remember this. A to the power of b times a to the power of c is equal to a to the power of b plus c. Okay, this is one of the fundamental properties of exponential functions. And so this is equal to 3 to the power of 3 over 2. Which means this is equal to log 3 to the power of 3/2. And that's why it's equal to 3 over 2. The exponent of this. Since the base is the same as this, 3 to the power of 3 over 2 will be 3 to the power of 3 over 2, right? So that's the way how we calculate. The most important is to transform whatever is under the logarithms into the base in some power. And we will do exactly the same in all these cases. Log 1/2 base square root of 2 over 2. What is it? It's log 1/2 of square root of 2 is 2 to the power of 1/2. Then 1/2 is 2 to the power of minus 1, which is log 1/2 2 to the power of minus 1/2, which is equal to log 1/2. Now, since this is minus, we can invert it, and we will have 1/2 to the power of 1/2, right? Instead of 2 to the power minus 1/2, we have 1/2 to the power 1/2, which is therefore equal to 1/2. Next. Exactly the same technique we will use all these times with all these calculations. Log 1/10 10 to the 3rd degree. All right. Log 1/10 it's 1/10 to minus 3, right? Instead of 10, we can put 1 over 10 with a minus sign in the power, in the exponent. That's why it's equal to minus 3. Okay. All right. Okay, so what is this? We have to really convert whatever is in the parentheses in an expression of 2 to some power, right? So what is, first of all, it would be negative power, right? So it's 8 would be 2 to the power of minus 3, because it's 1/8 actually, and 1 over 2 would be 2 to the power minus 1/2. So minus gives you 1/2, 1/2, and the power of 1/2 gives you square root, which is equal to, now you have to add exponents, so it would be 2 to the power of minus 3 and 1/2. And that's why it's equal to 3 minus 3 and 1/2. Oh, sorry. 3 and 1/2, which is minus 7/2. All right. A couple of more. Log base is square root of 3. 27 square root of 3. All right. So we have to convert whatever is here into the square root of 3 in some power. So let's think about it. 27 is 3 cubed. But if I want to have the base 1 square root of 3, which is this, right? So instead of 3, I put square root of 3 square. Now, this expression means you have to multiply the powers. So it's square root of 3 to the power of 6. So here we have log square root of 3 of square root of 3 to the 6 and square root of 3 to the 1, which is equal to log square root of 3 of square root of 3 to the power 7. So that's equal to 7, right? One more. Log base 1/3 of 1 over square root of 3. Well, again, the same thing. 1/3, 1/2. That's what 1 over square root of 3 is, right? This is the square root. And that's why the whole thing is equal to 1/2. Sorry, that's 3, supposed to be. Okay, that was the last one of this series, and then I have the last series of problems of the same kind of difficulty, or easiness if you wish. Well, actually they are much easier. So we're talking about common or decimal logarithm, which is the logarithm base 10. So the question is, what is this? Now, if there is no base indication, it means it's base 10. Well, you know that log of 1 with any base is equal to 0, because any base to the power of 0 would be equal to 1. Next, log 10. What is the power I have to raise 10 to get 10? Obviously 1. Log 100 is equal to 2, because 10 squared is equal to 100. Log of 0.1 is equal to -1. This is 1/10. So if I raise 10 to the power of -1, I get 1/10. And finally, log 0.01, which is 100ths, this is -2. Because 10 minus means it's 1/10, and then square, it will be 100ths. And the last one, log 0.001, obviously it's -3, for the same reason. 10 minus would be 1/10, cube would be 1,000ths. Okay, that completes the series of simple problems related to logarithms. Please re-examine them again. I think it's always useful, this type of things. As usual, I encourage you to be a registered student, to have somebody as a supervisor, or actually you yourself can be your supervisor under a different ID. Enroll yourself, or somebody should enroll you into courses, and that would enable you to take exams, which is very important. Thanks very much. That's it for today.